This video will focus on the learning target and explain what factors change dissolving rates and the solubility of solute. If you see this learning target, essentially it's a combo of two concepts: what factors affect dissolving rate and what factors affect solubility. Those are two very different concepts. Dissolving rate is the rate at which a solute dissolves into a solvent, and solubility is how much solute can dissolve in solvent. Some factors are the same between these two things, and some factors are different. Okay, every solution, every solute-solvent relationship has a maximum amount that can be dissolved, right? It has a solubility. We can affect that solubility, but affecting the rate at which it's dissolving doesn't always affect the solubility. So the factors that affect the rate at which you dissolve something are surface area, agitation, and temperature. So if I increase the surface area of my solute, essentially I dissolve faster. If I agitate, so stir or shake or do something to my solution, I make it dissolve faster. And if I increase temperature, I make it dissolve faster. In all three of these cases, the reason I am dissolving faster is because I'm increasing my dissociation hydration ability. Essentially, in order to dissociate and hydrate, my solute must come in contact with my solvent. Without any of these enhancements, of course, it will happen because of Brownian motion, but all of these additional aspects could make it happen more frequently. So increasing my surface area just means I'm going to have more contact between solute and solvent, so I can build those new IMFs more quickly. Agitation, again, allowing for fresh solvent to come in contact with solute, allowing for those IMFs to be created. And then temperature, same thing. I'm increasing the motion of my particles, they're hitting each other more often, and now I'm dissolving more quickly. When it comes to how much can be dissolved, two things can affect that: pressure and temperature. Pressure only affects solubility of gases. So if you increase the pressure on your solution, you can dissolve more gas in. Okay. You've all seen this before. If you walk down the aisle of a grocery store and you look at 2-liter bottles, you'll notice there are no bubbles in that pop. And that's because that pop is under pressure. You have all the carbon dioxide dissolved. As soon as you release that pressure, right, decrease pressure, all of the gas that was inside now becomes undissolved and it bubbles out. So essentially, under pressure, I can dissolve more gas. And the reason really is because of the compression aspect. Under pressure, I'm essentially compressing or pushing my gases, thus not allowing them to escape. As soon as that pressure is released, my gases do what they naturally do, and they become undissolved. If you think about this in reality, gases are nonpolar, and we're dissolving them into a polar thing. So technically, that doesn't really happen. It only happens if I can make my gases start to act more real, which is under high pressure, low temperature. The other factor that can affect how much can be dissolved is temperature. So temperature both affects rate of dissolving as well as how much. Okay. For gases, we find if I increase the temperature of my solution, I decrease how much can be dissolved. Okay, so it's an inverse relationship. And it should make sense, again, if you think about the fact that gases don't want to be dissolved and we need them to act real. We need them to have more IMFs, which is at high pressure and low temperature. So as soon as you start to heat them up and they start to move around more, we just have less IMF exhibiting themselves, and so we can't really build a solute-solvent relationship. So this graph shows for a whole bunch of different nonpolar gases, as I increase the temperature, I have a lot less solubility happening. For other things, we find usually it's a direct relationship. Okay, as I increase the temperature, I can dissolve more. And that mostly we think that's because we have increased contact, we have increased motion, and essentially we need less new IMFs forming to have them dissolve. So water is able to do more with less as it's moving around more quickly. As you can see from this graph, some substances are more affected by temperature change than other, right? Sodium chloride, you can't dissolve very much more in as I increase my temperature, but something like KNO3 increases greatly based on temperature change. If you look at the bottom of the graph, you'll see I do have one not following the trend. It's a very, very large ionic compound. And if you look it up, I believe it's an insoluble ionic compound. What we find with insoluble ionic compounds is as we heat them up, they're even less likely to dissolve a lot of times just because of how big they are and how insoluble they are in the first place. So in summary, agitation, surface area, and temperature all affect the rate, but they do not necessarily affect the solubility except for temperature. What that means is if you put solid in beyond the saturation point and you shake it and shake it and shake it, nothing's going to happen. There's no way to dissolve it beyond the solubility point unless you affect pressure or temperature. That's it. Have a nice night.